year, I plan to cover convert the course into deep learning, not machine learning, but graduate level will be deep learning. Purely deep learning, there will be a lot of variations next time, but not this year. All right. Okay, so let's get started. So even though this is not trendy, but I think it's a very strong baseline for you to implement and also for you to understand the data properties of text, which is a dominating data in almost every those IT giants company, right? Twitter, Facebook, Google, if you think about it, the main data they are handling are text data. Of course, now Google has more image data, and but I think Twitter it's pretty dominantly text data, and Facebook too. All right, so again, so our nutshell, and we are using the joint probability instead of conditional probability. It's joint probability of x condition C times PC to perform the classification, and we have covered the Bernoulli type of model so the differences is really in how do you use model, this generates a model when you condition on each class labels. So we already covered the Bernoulli model. We also covered Gaussian model. Actually, in the Gaussian case, we have naive version and also the non-naive version. And today we're going to cover, it's called the multinomial naive Bayes classifier. Okay, just to recap, when we talk about a generative Bayes classifier, what we truly estimate is for each class label, we have a generative model. And we need to estimate the parameter for each possible class labels. And at the same time, we need to estimate the priors of each class too. And we're using that this decision functions to perform. This is the MAP decision function to use this rule to figure out who is the most likely class. And the naive Bayes classifier, in fact, just having the assumption of this joint conditional probability of x1 to xp is equivalent to each of the marginal conditional probability just times together. All right, so this is today's content. So I'm going to first talk about how do you represent a text document. And then there's will be two models, two naive Bayes classifier models which are normally popular to represent text data, to perform text-based prediction models before. And the first one is called multivariate Bernoulli model, and the second is called multinomial Bayes classification model. And so for each of those, I will talk about how do you test, how do you train, and then this is exactly how you're going to figure out or implement in the homework 5. All right, so this has a lot of overlaps if you're taking information retrieval or you already took text categorization course. But I still want to cover this because it's fairly basic, but a lot of students, if they never took text retrieval course, they don't understand this. Maybe let me just roughly give a guess. So who hasn't learned about bag of words representation? Can you raise your hand? Oh, well, who hasn't learned? Okay, pretty small number. Okay, so in the end, just the basic task is to classify a text article into some classes. So for example, in the classic case, is spam email classification. So the input is this email, the full email text, and output is this a spam or not a spam? So in fact, like if we're using probability type of model, we're predicting P, C condition on the document. So here, so I used to use X, but just let me use D this time, just representing this as text document. So let's just again talk about history. So why non-based? Similar to any of the other classification model which kind of dominating at a certain stage before. All right. Yeah, so let's go on. So in this literature of data-driven models, and it's always because of competition winning results makes the some classifier kind of dominating. In the case of naive Bayes, it won the competition in KDD Cup, which is pretty old, of course, 1997, in a text, a mail-based. Alif, can you help me check? So this is really just trying to predict if a recipient of email will actually respond to an advertisement. So there are about like 750K records in that competition. So this is very, very big amount of data in 1997. If you still remember this year, this is a very magic year for the deep learning. The convolution neural nets was kind of designed or first out by Yang Wukong in 1998, and the recurrent neural nets was out in 1997. But both approach could not just even, they are just too difficult to implement, and at that time it's actually is decision tree and naive Bayes, and then later it's SVM dominating the whole industry, so performing data-driven predictions. So naive Bayes is a very good, solid baseline for text classification, but not the best. And for most text categorization, the main issue here is there's certain properties is for text-based classification, there are many relevant features, but also there are many irrelevant features. So which type of method, if you think about it, can handle or nicely handle when you have so many features? Some of those are relevant, some are irrelevant. And also the relevance among the useful features are quite similar to each other. All right, so just to give you a few examples of other type of text classification applications. Yeah, so we can perform spam email classification, web page classification, which was actually a very classic task by then. And we're going to have an example to show you. So, and then there's news categorization, which is predominant. If you think of Google News, it's a very, it's exactly doing this automatic news story classification. And the movie reviews, which is the sentiment recommendation, which exactly is this type of classification. So actually, in fact, in the literature, so how do you even know what task is important? Researchers just design and think and then propose. For example, sentiment classification was never even used before by those IMDb, but just one researcher from Cornell, they just think, why not? Can you do a text-based polarity prediction? And then immediately Netflix and Amazon Reviews or TripAdvisor realized, wow, such a great tool can ease the whole pipelines of their running. So they adopted the sentiment classification, which becomes a dominating application now. So yeah, like email classification is also a dominating function, and almost every email provider is using now. Okay, so this is just to show you an example of Google News classification. This is actually what I just captured like 2 hours ago. I mean, Google News just automatically categorize the news into categories, right? So this category, in fact, it's more like a tree, a shape of a tree. And I'm just using science today, so NASA, and then this actually it's pretty easy if you feel like there are certain special words. It's most likely to be appear in the science category, right? There are certain kind of words most likely to appear in the politic type of kind. So that's the basic intuition behind text classification. Okay, so first question is, how do you even represent it? So your text articles are input as just a string of words, and the string of words, I mean, you don't know its length, right? Because different news articles, there are some shorter, some are longer. How do you represent it? So the issue just how do you represent it? So in the end, the most classic representation is called bag of words representation. So that's the problem. You want to classify this article or this piece of reviews into a class. And then this is how you truly represent to a classifier. So in here, you're saying, I love the movie, it's sweet, and then whatever, it's great. And then here, you actually just forget about the concrete phrases or whatever. You just leave a vector with a fixed size, which is the dictionary size. And for each entries, it corresponded to a specific word in that dictionary, and the numbers they are representing how many times the occurrence of that specific word in the article. This is called a bag of word representation. And then you're just performing the predictive models on this vector formulation. So, but how do you convert this into this? There are a few steps. So when we are giving you this data, so the data is just a lot of different articles, right? Some are classified as positive, some are classified as negative. And how do you convert each article into a vector? And the first question is, who is even that dictionary representing? And how do you get the dictionary? So in fact, this is a very difficult step. So in the homework, we give you a simplified version, which is predefined 16 words. Honestly, this is a very bad, weird choice. The reason is just for those students who can't, who doesn't want to mess around with NLTK, you can just go with the 16-word choice. For those who actually want to play with NLTK, please do so. Okay, so in NLTK, you need to figure out, it's actually pretty easy. The library is very mature. It needs to perform first to remove the stop words. Stop words is mostly likely is those words really doesn't have any meaning at all. So for example, maybe or a. To have this word, I mean, it really doesn't tell you anything, right? So in a lot of cases, this is removed in the dictionary, from the dictionary. There are a lot of other words like is. I think some cases is kept. It depends on this rule of what it's strict or it's less strict. There are different variations of stopping word removal. And then, so this is the first step. After you remove the stop words, and then you have to convert, for a word, you normally have different appearance, like love, loves, loving. You want to match it to the same word, love. So this step is called stemming. And in the NRTK is the tokenizer. there are actually multiple different tokenizers. Again, play with it. And yeah, so you can go with the choice that directly using NLTK to construct a good dictionary, or you just use the weird small dictionary we proposed, and that's totally good too. Question about this? Because I already see a student propose like a posting question on Piazza about this. All right. Okay, so now you have a dictionary, and then you need to do counting. You need to count how is each word appeared in a specific document. That specific document is your sample, a sample, right? You need to do this frequency counting of each word in the dictionary. Yeah, so assuming your word dictionary is W1, W2, until WK, and that's your dictionary, then you can represent the text into a vector of word frequencies. So, but this is actually just one possible choice, right? You can also make an even more simplified choice is you just check has that word appeared in the article or not? And the only thing you recorded in the vector is yes or no. This makes each value or each entry of the vector into a binary representation. And even more, you can convert the count, or you can use some kind of normalized count. There are many choices. So the popular choice, this is actually there are many papers in information retrieval just to trying to figure out what is the right number or right way of numbers to put as per word appeared in the article. So very classic is something called BM25, and it's actually TF-IDF date. I don't want to cover more, just feel free to check it out. But I think in the homework, let's just use the count. Used count is good enough. But I want to let you know the state-of-the-art information retrieval systems not directly using count. It's something relevant to count plus some kind of normalization. All right, so now you get, for your data, you're getting the matrix now. So now that many files, which is the one we actually shared you, each file converted is the per file, right? It's per file, it's per sample. Yeah, I remember. So each file there becomes a row in a matrix form. And each row representing a specific document. And in here we have 0 until 900 document, just to show you a rough, speculated number. And each column here showing you the dictionary words. About the dictionary words, W1, W2, until W, I think we use the capital B or capital D to represent the size. Maybe B, yeah. All the possible words, so each entry xij is just the frequency of word j in the document I. So now this is a matrix form. Then you can just apply, anything can be applied on the matrix form to perform prediction. So yeah. So the issue is, first of all, the vocabulary size, it's actually very tricky. So if you have too big vocabulary, so assuming let's just don't even use NLTK, forget about all those stemming, forget about stop words too, you really just use a hash function. The simplest, just performing hashing. Do the hash array, put whatever unique string labels from your current data into a hash. And that's actually your dictionary, right? Because those are the unique string. The unique strings happen in my data. However, this is a bad choice, so they're most likely, just like the one I just showed, love, loving, loves, the three things match to three different unique hash keys. But in fact, they represent similar semantics, right? They should be matched to the same hash key. So that's the first reason why it's bad. The other reason is this type of hashing or uniqueness-based dictionary building will have a lot of those unique strings appeared only once, appear only or even only twice. It's really difficult if you observe it only once or twice to estimate, to perform a solid or credible justification about its frequency, about its probability, conditioned on a certain document, and then hopefully to generalize better. So that's why the real word is a bad thing you want to avoid when you handle the text data. So, which easily you can do using the hash. You use the value of each hashing as the frequency, right? That's the easiest way to build this dictionary. And then you're just cut. So the pretty classic approach is after stemming, after removing the stop words, and then performing the hashing, and then sorted by the frequencies, you normally try to remove, you should remove those words appeared smaller than maybe 5 times in the training data. So it's just a magic 5, give you a good practice. Okay, so this gives you the training data dictionary, right? But that's just my training database dictionary building. When there's a future text article coming, it's highly likely, and there are words just can't be matched to any of the dictionary words you have. How would you handle it? So this is just classic problem, or very, very classic problem called out of vocabulary problem. And that people just use this a strategy called unknown. So I'm adding an unknown token in my dictionary. Whatever is rare, whatever is unknown, I will assign unknown as its token. Okay, question about this?
What if you have 2 words
2 words
that are unknown?
and 2 times. Put
okay.
frequency as 2. Yeah.
Does it matter if can I just ignore the word? Or
Good question. So I think in our setting we should ignore it, right? Or we should have it. Because our dictionary is so small. I don't remember that. Yeah, let me recheck it. It really depends on your dictionary. If you think about, if my current dictionary can cover 95% of the words in my current corpus, and the unknown represent the 2% left, right? That's fine. I mean, if I ignored it. However, if your dictionary covers only 10% of your current article, then 98 will be unknown, which is really bad. I mean, I think this is our current choice. We will fix it, and I think in that setting is you ignore it. Yeah, yes, in our setting actually ignore it, because unknown is kind of dominating, which means we just assume all the unknown are the same, and we ignore the unknown in the calculation of the classification. But if you use an LTK, don't do that. All right, so too slow, but I want to get a really careful discussion and hopefully to help you to finish the homework nicely and also got a deeper understanding about handling this type of data. So there are 2 different probabilistic models. One is called multivariate Bernoulli and the other called multinomial. So what do I mean multivariate Bernoulli? So the equation on the bottom is the equation we need to use, right, in the generative Bayes classifier. And if we want to use generative Bayes classifier, so let me just, again, using our notations, still CI, and then I'm converting just using D to represent as a document. For a specific document, I just converted, it's the same PCI times PD conditional CI, so this is the one I need to estimate for a specific document D. Then how do you represent this? Because we always know how to represent PCI, right? That prior probability, which is very easy to estimate. It's just a count of a specific class over all the possible occurrence. So there are two different ways you're representing this, which is related to the background word representation we just reviewed. You either represent this as probability. So this is if you representing it as count, this is a count-based formulation. And then if you represent it as a Bernoulli, and this is the Bernoulli, you need to figure out how to represent it, right? So the first kind, which is exactly, if you use the naive assumption, which is exactly the multivariate Bernoulli distribution. We're using a multivariate Bernoulli distribution to represent this joint conditional formulation. For the second kind, we're using multinomial distribution to calculate the second kind. Okay, so then what is this? So I'm going to talk about what are they after a few slides. So first, let's compare. So multinomial versus multivariate Bernoulli, so why, based on the 1997 until 2005, there are actually a lot of papers compare this. The multinomial model is almost always more effective in the text applications. So this maybe sounds so trivial, right? But you need to think about maybe in the future you have some kind of discrete type of features. Consider maybe use the counts. This is not just to text, right? Consider use the count, not just use exist or not. So especially in a lot of system or security type of formulation, actually people use this multivariate Bernoulli model a lot. Is this PDF comment section that exists in my PDF documents or not? Or there are actually a lot of those type of models even now in a lot of domains. Yeah. All right, so it's actually from Chris Manning. They compared, and the comparison it's on this quite simple toy task. So for university homepage, you want to classify it as student, faculty, and other things. And it just hand crowd 5,000 hand labeled web pages from Cornell, Washington, UT Austin, and Wisconsin as a training, and you apply and crowd classify as from the sites from Current and Allen. And so this is the figure they compare. So actually it depends on the vocabulary size. When your vocabulary size is pretty small, actually multivariate Bernoulli is better. When your vocabulary size is kind of larger and larger, in this case is 100K. Yeah. So even though we have only 5,000 training data, but actually the dictionary size here is huge, right? Dictionary size is 100K. And this is very classic for text classification used to. It's a huge, high-dimensional task. All right, so now let's see what is multivariate Bernoulli, which you already learned. It's exactly naive-based classifier, and each entry is a Bernoulli variable. So now we have this Bernoulli vector, and each entry shows a Bernoulli variable, exist or not exist. And then you're trying to representing this joint vector condition on each class labels, right? So first, let's see the assumption this representation making. The whole assumption is one word in the document tells us nothing about chances that another word appears. We're going to use a naive Bayes assumption to decompose this joint probability into multiple conditional probability. So we're going to So this is the model. The naive assumption here actually means one word appearing in my document tells me nothing about another word appears in the document, which is actually apparently not very good, right? Yeah. All right, but that's all you can do, right? Because otherwise, how can you even estimate? This is exactly what we had in that tennis example, right? You need to have all the possible combinations, which is 2 to the p, and to count each case inside 2 to the p from your training data. There's no way. Right? Just let's again see the size. Labels is about 10,000, p is about 100,000. 2 to the 100,000. There's no way to estimate that. You have to convert this into, because this is one of the question, right? If I'm doing naive, how many parameters do I need to estimate? Assuming there are only two classes.
2p.
2p, right? So in this case, 2p is how many parameters? Assuming p equals to 100k. 2p is 200k. And then how many samples do you even have? 5,000, which is still pretty short if you think about it. And we need to make assumption to extremely simplify. Just the reason is the space is super large. All right, so you do conditional independence assumption. This equivalent to this multivariate model be decomposed into p independent Bernoulli variables. And then this is exactly what we showed in the naive Bayes classifier. You can use a graphical model representation using the class label as the parent. Every every features is a children node in this representation. And then the joint conditional probability becomes the multiplication of each marginal conditional probability. All right, so how do you estimate each P1 equal to true condition C or PW whatever double, right? PWI condition on CJ. So this is because of Bernoulli, right? And as long as you know P hat and it's enough to know the Bernoulli distribution, and then you need to estimate PWI condition on CJ, J from I from all the vocabulary words, and J is from 1 to all the L classes. So we actually had all talked about this already because and this is the matrix you're going to estimate. It's a matrix with I use K here. It's actually just the vocabulary size. Yeah, and just use K to represent vocabulary size. And then it's a matrix. This is your model. This is the model you need to estimate from data. All right, so I'm not going to cover this, but I hope you can read this. Is how to estimate Bernoulli variables parameter P hat. And the whole idea is maximal likelihood estimation, and assuming just you observe hat, and then to the tail. And then you're representing each observed data through this formulation, P to the specific, is it head or is it tail? And then, because you're observing n of those, right? Then you just multiply, so your likelihood is multiplication from the first observation onto the nth observation. For each observation, that's the probability through that through this Bernoulli probability formulation. And this formulation can be easily converted, so because this is a multiplication, right? And all this under the power, they are all p, and this becomes what? P to the summation of xi, and 1 times p to the summation of 1 minus xi. Right? It just, for all the observations, you observe x1, x2 until xn, they are head, tail, or you convert them into 1, 0 form. And each one of them has this, and then because multiplication is equivalent to p to the summation of xi times 1 minus p to the summation of power of summation of 1 minus xi. And because for those xi equals to 1, this is what? Summation of xi, because xi is this representation, right? Xi means if its head is 1, if its head is 1, if its tail is 0. So summation of xi is what? It's the number of times heads appeared in that n trial. All right. So this is the likelihood. The likelihood is p to the number of times in total has appeared in my n trials, and then times 1 n minus p, n minus the x. So the number of times tail appeared. So this is the likelihood. Then you optimize this likelihood by maximize it and looking for the best p, right? How do you do it? You take a log, and then this is what you get. And how do you maximize this? How do you maximize this? How do you maximize a function? In taking gradient, you set it to 0. So in this case, take a derivative versus p. You set it to 0, which is next page. And every step is there. You take a derivative versus p, and this is what you get. Hopefully you still remember how to take a derivative of log function. Okay. And this is you get the derivative, you set it to 0, and then just with simple derivation, you're going to get this equation, and then this equation, and you get the best p is number of times head appear over the number of times you flip the coin. So even though we always use p over n, but this gives you a solid proof. Why? Because it maximizes the data likelihood. Okay, so feel free to read it. So it's very easy to prove this. I mean, everything is included. All right, so now how do you estimate for a specific word, condition on a specific class? And you just do fraction of the document of label CJ in which word I appears. So those documents has the W and their label is CJ on the denominator. In the denominator is the number of documents in your training data. And then when there's a new document coming in the testing state, how do you do it? So you should also know this very clear. It's really a lookup operation, right? The 10th example is exactly the same as this, but a little bit more complicated because in the 10th example, each variable, it's not just binary. There are also choices, maybe 3 possible choices. In this case, there's only 2. So that's why you have only 1 parameter, and the other case it's just 1 minus the p. So it's a simpler case. Okay, so but that's not enough. So you know the training, you know the testing, but it's actually not enough at all. You can just do perform this calculation, and I actually talked to you about it. When you have a lot of words, that joint probability is many smaller number, small positive number multiplied together. And this easily have the overflow problems, the numerical problems. And you can't, it's just not stable at all. So that's why, in fact, what we truly calculating is not PC times. So what we're doing is not actually the previous page. It's not this page at all. What we're truly calculating is actually this page. It's every number needs to have a log there to make sure it's numerical stable. The summation of logs, to avoid this numerical problem. And then you just do argmax. The reason why you can do log is because log is a monotone function, right? It doesn't change the argmax result at all when you're performing a monotonic function on each entries of the comparison. Question about this? All right. Okay, so now I'm going to talk about multinomial naive Bayes classifier. So I hope you still remember what is multinomial from your probability class. So in the end, what we're trying to get is this joint conditional probability. So all this vector of counts, what is the probability given a specific class? So in this case, words are like a colored balls, right? There are k possible color balls. In this case, actually, it's the vocabulary size. And in total, so for a document contains n words, a capital N words. Each word occurs ni times, like a bag of n colored balls, right? How do you represent its probability? Very classic representation of probability function to model this type of count vector is the multinomial distribution. So before I talk about multinomial, let's cover binomial because we understand Bernoulli, and then Bernoulli is really just let's see. So the binomial distribution is a count of the success of events over n. So if you flip a coin, you flip n times, and the distribution of how many times the heads appeared is a binomial distribution. So not to get you confused, we just covered you HH or TH onto maybe H. You just flipped, you actually flip the coin for n times. And the number of times is the head. This is a random variable. Actually, this is the random variable. This number of time a head appeared is a random variable. This random variable is its distribution is the binomial distribution. Don't get confused with Bernoulli. Bernoulli will only represent the probability for a single throw, flip the coin. Is it a head or is it a tail? And here we care how many times head appeared over n flipping coins. It may only appear like maybe one time, two times, until n times. So all the possible numbers of this random variable. Let's just treat this random variable as x. X is the number of times head appeared through n times of flipping the coins. X, what's other event space? Let's remember, whenever there's a random variable, you need to understand event space or elementary event of a random variable, right? What is the elementary event of this random variable x? 0 to n. Yeah. So For the Bernoulli variable, what's the event, elementary event for the Bernoulli variable? Head and tail. So try to be clear about the differences of both. So Bernoulli, it's about count. Okay? And when you're trying to figure out the Bernoulli distribution is, you actually have the two parameters. First is actually that n, so how many times you flip the coin. And the second is the p. So for each flip the coin, what's the probability it's a head or it's a tail. So, and n head plus n tail equals to n, and the p head and p tail summation equals to 1, right? This is binormal distribution. Then you just extend this into multinormal distribution by allowing not just 2 events, but actually allowing k events. In this case, like roll the dice is 6 events. In our case, the dictionary, our dictionary is much larger, and you're calculating each possible elementary event, it's a number of occurrence. And this is what you're observing. And the multinomial representing this joint vector representation, joint vector probability. Of course, it needs to satisfy if the first appear n1 times, if the second elementary event appear n2 times, n1 plus n2 until nk equals to n, because that's the whole number of times this you perform the throw of the dice or the flip of the coin. And also the probability, so the parameter of multinomial distribution is this total number of n, and also the probability of each elementary event appears. So in this case, it's theta 1 until theta k, and theta 1 times the summation of theta 1, theta 2 until theta k is 1. And the parameter in the end, in this case, is this theta 1 to k vector, probability of each elementary event, how likely they appear, and the parameter of number of times you observe that event. Okay, and then how do you write this joint probability, which is super easy, right? I mean, we actually always remember that because the first elementary event, the probability is theta 1 condition C, and I observed it n1 times. Of course, it's just n1 to the power of n1, right? A theta 1 to the power of n1. Then the second event, second elementary event, is theta 2 to the power n2 until the theta k to the power of nk. And I hope you remember this term because so anyway, this is the possible ordering and the factorial over all the other factorial because we don't care about the ordering. Anyway, so however, in our case, because this term is, so what do we observe or try to estimate from data? If I want to estimate this multinomial distribution from the data, what is unknown? So I already said, right, for multinomial distribution, what you need to know is first is the whole number of times you observe the event, right? And the second is theta 1, theta 2, until theta k, right? So then condition on the C. And this is actually the model you need to observe. So let's assume this is called theta. N for each document DI, you actually know the N. You know the full length, right? That means this is the number of times those color balls or this word article appeared. How do you see the different words appeared, and they appeared n times in total. And you actually know this n. You don't need to estimate it. It exists for every document. And then, but you actually do not know theta 1 until theta k. condition on the C, right? You need to estimate this from data. So when you're doing argmax, and what matters, this N is actually the same for every article. When you perform for a specific article, the N is shared, and N1 and 2, they're all observed, so that's why you don't even need to do this, perform argmax, because for different classes, this parameter is shared. So in the end, this portion is not related to C. That's why we don't need to use it. That portion is not relevant to a specific class at all. And the only thing you compare is this quantity. Question about this. And this is how you get the joint probability, right? The joint probability is this scalar, because it's not relevant to C. And when we're performing classification, what we do is argmax, right? It's argmax over C. E W1 equals to N, N1 into WK equals to NK. Condition specific C, and then times PC. And you just substitute this thing into here, and because you're doing argmax over C, and this quantity is not relevant to the C at all. So that's why this is the one you use to perform classification. This actually saves a lot of calculation. Because they are labeled invariant. And then the model you need to estimate in the end from the data is theta 1 onto theta k, condition on C1 onto CL, and this is the matrix you need to estimate. This is your model. The multinomial model, you need to learn from the data. Question about this? All right. So this is exactly trying to show you the testing rules. So what MAP formulation you're using to get max C, and this is the rule you're going to use. This is the testing stage, which is what you're going to implement. Of course, what you should implement is the log version of this, right? Right? So now let's see, how do you estimate those from the training data? So I want to estimate this matrix from data, from my training data, and this is a K times L number of parameters, right? So same thing. So how do you estimate multinomial distribution? Assuming, so just to simplify, this is not condition C for now. So there's no condition C, just from the data, how do you estimate multinomial distribution? Maximal likelihood estimation. You just substitute this and D, it's really just that W, right? Each specific document is the word first is equals to N1 for the document T. W2 is N2 in the document T onto WK in the document T. Right? That's actually D in the representation. And then you just use the multinomial representation, you substitute here for each document represented as a multinomial joint probability. And then again, this is even not relevant to the theta. It's not relevant to theta. You perform your argmax, you just cancel this out. And then this is the one you maximize over all the documents. Subject to summation theta 1 theta 2 onto theta k equals to 1. Okay, so how do you maximize that? You have theta 1, theta 2 onto theta k, different parameters, and you have one loss function. So this is a little bit hard. I'm not going to cover that. There's an extra document. It's actually not very difficult too, because you can decompose this to be only just related to each of the theta. And because this is called a constraint optimization, which we covered a little bit in the SVM formulation. It's actually not hard at all. Is to add this part into the loss formulation through a Lagrangian multiplier. You're just trying to maximize things together. You take gradient, set it to 0, and you're going to get the theta I for a specific elementary event. For a specific elementary event, the MLE solution is, so over all the samples, in our case, over all the documents, the summation, the number of total counts that specific elementary event, that specific word appeared, over the summation of every sample. So this actually means this is the whole length, how many times, it's really just the length of your whole training data. And so assuming this is actually not considered a class label yet, right? Just when given that data, you try to estimate a multinomial distribution. There are multiple text samples, and this is the full number of word count of that data. And this is the number of word count of that specific word. And this means what? To perform multinomial distribution is actually extremely easy. So again, just to clarify the context, we're not conditioned on the C yet. We're just giving you your data. How do you estimate multinomial distribution? I'm giving you multiple text samples and a dictionary of W words, right? W1 to WK words. Very easy. You don't even need to care those different samples. You put all the samples together, create a mega document, and then you just, upper is how many times this word appears in this mega document. The length of your mega document is the probability of theta I for that elementary WI. So so I'm trying to repeat it. We can create a mega document by concatenating all the documents D1 to DT, and then use a relative frequency of specific W, a specific elementary event, and then this gives you the multinomial specific theta for that specific W. Okay, question about this? It's hard to ask a question unless you perform this the MRE solution, but feel free to do it by yourself. And this takes a little bit more time. All right, so now let's see. We use multinomial distribution in when we have a C variable, which is, so I should actually write C. So what I'm conditioned on, I should have theta 1, let's see. Yeah, so this is D1 to your training data. I'm trying to estimate this matrix. And this matrix is, again, W1 to WK times C1 to CL. And how would you do that? So you just, for each class C labels, you create a mega document. For each class C labels, you create a mega document, and then you just, you count how many times the W appears in each mega document, and that's how you get P. That's how you get P W specific I for a specific CJ. It's a very easy solution. It sounds very complicated from a machine perspective, but in fact, its training and testing is extremely simple. Yeah, question about this? There's a little bit. Yeah, this means the WI, specific WI words, and this gives you the theta, WI, and CJ. All right, so yeah, just kind of repeat it for a specific C, and you just yeah. So yeah, I think this is more concrete. You can read it when you implement the algorithm. This is just more like a flow representation of how you implement training. Okay, just to summarize, naive-Bayes model is actually not very naive at all. It's a very solid baseline for text classification. It's very robust to the irrelevant features. It's also very good to, it's a very good approach when you have many equivalent important features. And it's a good solid baseline, and it's optimal if the assumption holds. And the other big reason is it's super fast. It's actually super fast. So think about how do you implement this? Yeah, let's go back to this algorithm. How would you implement to get this matrix? It's actually super fast. You only need to go once. One pass of all the training data, you can actually get this. So for class, you know the class label, right? You just concatenate whoever being classified as C1, create a mega document, and then you loop over each word through that mega document if it's a hashing, right? If in the W1, W1 got +1 count. If it's W2, W2 got +1 count, right? Think about this. For the C1, you got a mega document. You create a hashing. You just remember, keep just +1 when you meet W1 or maybe WK, whatever. Just one pass of the C1 document. You got that column vector. Then you do the C2, C onto CL. And this actually means only one pass of all the data. And the cost is, so assume you have T documents, the average length is TD, the cost is only T times LD. And yeah. Oh, I see. I think you need to normalize it, right? Yeah, there's another cost. Okay, so this is the handling the training data cost, right? You touch each word, doing this sweeping operation over all the documents, and then you got that matrix. So after that matrix, and then you need to do normalization, right? That normalization touches every entry of that matrix. And the size of that matrix is C times V. It's the number of words times the number of class. And this is super small, actually. TLD plus CV. And the test time is actually pretty quick. So you're really just for, so that's a matrix model, right? W1, W2 until WK or V, which is the same thing, C1 until CL. So when you perform test, it's actually the same thing, right? You need to convert your testing data into this vector form. But you don't need to do backwards representation at all. You only need to count. Yes, actually that's true. So in let me see. This is in the testing stage. So let me ask you. Yeah, this is the testing stage. how do you implement this testing state? How do you implement it quickly? So there's one way, there are two different ways, right? The first way, when you are given a document, it's a document, just a sample. It may be like double I words and double J words or whatever. It's not a bag of words representation. Let's start from there. Until the length, maybe represent length, maybe that's specific L. So how do you represent this testing calculation? So there's two ways, right? The first way is you convert it into bag of words. The second way actually is what? Don't even bother. For each class C, I do PC. If I meet the first word, I'm calculating that specific first word's probability. And then I move to the second word. And just times that second word's probability. And I don't even need to have the backward representation. It's just PC times P first word I met, the position, P word, the third word I met, P2, until the last word I met, P, maybe L specific D. And this is actually equivalent to this. And this is a homework. Yeah, it's actually very easy to derive this. And this computation of this is actually faster than this. And you can derive it very easily. How do you perform backward words? And using this versus no backward words at all, you really just loop over all the words, and then using the parameter you estimated and one pass. And this is all the length of, that's exactly what we showed in here. The cost of testing is C times of the length of the document. All right. Okay, there are 2 more minutes, and I really want to do something. So this is the last page. What we covered about everything we covered about generative model is already covered, but I want to do a summary table comparisons. So we covered the Bernoulli, we covered Gaussian, we covered the multinomial, right? So let's just see model. The models we covered. The base classifier and the full discrete case. And then we covered naive base discrete case. And then we covered Gaussian, the naive Gaussian. Then we covered LDA. Then we covered QDA. And then we covered multinomial. So this is really a lot of models. They're all in this generative base classifier category. All right, so let's just assume each of the xi, let's just assume the simple case. Can you hear me? Hello? It's okay, let me shout. Yeah. So assuming this is equal to 2 case, there are p different variables. Each one of them is x1 onto p, and each one of them is there are 2 possibilities. Xi equals to 2, and then this is also xi equal to 2. And the Gaussian case is, okay, let's just do, yeah. So the first parameter you need to estimate is PCI or PCJ. Let's use J to distinguish J from 1 to L.
So no matter what model you do, you need to estimate that OL parameter prior, right? This is just, it's not change, it doesn't change at all to whatever generator model you estimate. This is the prior distribution from the data. Okay, so what differs them is in this conditional joint probability, P, x1, x2. Here I'm trying to show the size using an asymptotic form. So x1 onto xp, condition on each cj. And then this is the other number of parameter I need to estimate, right? So, and we actually reviewed in the discrete base classifier, generated base classifier case, there's no assumption I'm making. I need to do an enumeration of all the possible tabular counting, right? So how many number of parameters I need to estimate in the discrete full joint case? If you still remember, each one of them have two possibilities, and then x1 onto xp is 2 to the power p. Also, because generative model is conditioned on each class labels, right? Which means for each class label, I have 2 to the p parameter to estimate. Which means the number of parameter is 2 to the p times L. Okay, question? This you already know because it's asked. So when you have a naive assumption, they are all independent from each other, which makes the number of parameters in each, there's only 2, and I have p of variables to estimate. This makes the full number of parameter is 2p times L. So this we already covered, right? All right. And then let's see the naive Gaussian case. So I hope you still remember the Gaussian. Gaussian is really this mu1. Let's just use, it's a Gaussian distribution, mu1. And then in the naive case, we are assuming the sigma covariance matrix is diagonal matrix, right? Then how many parameters do I need to estimate in this case, naive Gaussian? For each class, I need to estimate mu, which is p parameter, right? The size of mean vector is p. And then the size of the diagonal matrix is, because it's diagonal matrix, right? Each matrix, this matrix is p times p, and this vector is p times 1. And because it's a diagonal matrix, which makes the number of parameters we need to estimate in the naive case is, and then even further, the LDA case, we have different mean vector, but we have shared covariance matrix. So which makes the number of parameters we need to estimate is p plus, actually, no. So because I need to estimate a mean vector for each class, right? That's p times L. But I only need to estimate one covariance matrix because LDA assumes covariance matrices are shared. So that's p quadratic, of course, because the symmetry matrix, that's just over 2. Not completely correct, right, if you think about this, because, yeah, the diagonal terms, it's not overcounted, but that's fine. So in the QDA case, we have every Gaussian has its own mu and also its own sigma, which makes the number of parameters is p plus p quadratic times L. All right, and now it's the last one we do today, which is the multinomial base classifier, which we write it as theta 1 onto theta k, condition on the c, the specific c. The number of parameters we need to estimate is the vocabulary size, which is Yeah, so that vocabulary size V in this case, then times the L. And if you look, the naive, in fact, this 2, I put it there, this 2 should be replaced into V2, right? Because it represents a Bernoulli case, but you can also expand it into like a dice or K cases, which more correct representation here is not 2 to the P, it's actually K to the P. Yeah, okay. Alright, so this is everything I want to cover for generative base classifier. Thank you.